Hey there, it's Mr. P, and we're going to go ahead and continue our discussion of waves and continue in our wave unit. So this would be section 17.4, which would be today's the lesson here that we're going to look at as part of your e-learning for April 15th, Wednesday, April 15th. And so we're going to focus today specifically on sound. Okay, so sound waves are one of the are actually longitudinal waves, which remember those are one of the two major types of waves we talked about, where waves, the particles and the waves move parallel to the direction of the wave. So let's just go ahead and start with that. Okay, so sound waves are longitudinal waves. So remember, think of the sound waves moving from a sound source, and they move parallel to the particles of the wave, move parallel to the direction of the wave. And sound waves, think of as, I want you to think of them as vibrations. Remember, waves are disturbances of matter, and sound waves are all, same thing with sound waves, they're just disturbances or vibrations, and we'll see later we interpret those vibrations as certain frequencies and different intensities, and so a few aspects of sound we're going to look at: speed of sound, which we'll get to actually in more depth and later on. Frequency, pitch, intensity, loudness, so some things we're going to look at with sound. So speed of sound, first of all, okay, is one thing we want to consider with the speed of sound is that it takes time for sound to travel from place to place. Okay, so when we hear something, we don't hear the sound instantly as it occurs. It takes time for the sound to travel to our ear, and we'll see, in a later segment how sound enters the ear and how signals are sent to the brain that help us interpret the sound that we hear. But we want to make sure we know that it takes sound time. So a sound occurs, we don't instantly hear it. There's a delay between the time the sound occurs and when we actually hear it. Remember, speed in general is the time, the distance something travels in a specific period of time. And speed of sound is just the distance sound traveled in a specific period of time. And in dry air at 20 degrees Celsius, which would be about 68 degrees Fahrenheit. So room temperature, basically, is what we're talking about here. The speed of sound, 343 meters per second. It's about, in miles per hour, it's like about 750 miles per hour approximately. And, you may hear the term Mach, like jets fly at like Mach 1 or Mach 2. Mach 1, that just means speed of sound. If they say like something moves at Mach 2, you may have heard that. That just means twice the speed of sound. It's the fancy term for it. But sound, the speed of sound varies. So it's different in different mediums or different materials. Okay, solids, liquids, gases. So in general, sound waves travel the fastest in solids, slower in liquids, and the slowest in gases. Remember, air is made up of gases, so air would fall into that category. Okay, so sound travels a lot faster in a lot of different materials other than air. So particles in a solid tend to be closer together than particles in a liquid or gas. Okay, that has an effect on the vibrations and how fast sound moves through. So speed of sound depends on the density, so how dense a material is, and how elastic it is. So basically how flexible it is. So density and elasticity, how flexible something is, those two things determine the speed of sound. And again, we travel the fastest with speed of sound in solids, slower in liquids, slowest in gases. Let me show you a quick graphic that shows you the speed of sound in different materials. So we can see there 343 meters per second in air that's at 20 degrees Celsius, and some other examples of the speed in different gases. And if we move down to liquids, we see that sound travels faster. Like in water, sound travels 1,482 meters per second. So a lot faster than in air. And if we look at solids, okay, wow, we look down at steel, 5,960 meters per second. So again, sound travels the fastest in solids. And, you know, slower in liquids and the slowest in gases. So that's just an example here of showing the difference between the speed of sound in solids, liquids, and gases. All right, so let's go back to our notes. So another aspect of sound we're going to look at is the intensity of the sound. Intensity of sound. So it's the rate at which a wave's energy, remember, waves transport energy, so it's the rate at which a wave's energy flows through a given area. Sound intensity depends on the wave's amplitude, okay? So remember, amplitude is related to the energy in a wave. We talked about greater amplitude or greater height, right? The height of the peak above the rest position. Greater height, greater amplitude means greater energy. And in terms of sound, we're going to see that greater amplitude or greater energy means greater intensity. So sound depends on amplitude, the wave's amplitude, and how far we are, the distance from the sound source. Okay, remember amplitude, the height of the wave above the rest position, maximum height or maximum displacement. So this wave here would have a greater amplitude than, let's say, this wave, which would mean if this was a sound wave, we'd have more intensity, okay? Or we'll see later, it would be a louder sound, okay? More intensity in this wave, more energy than in this one because we have greater amplitude in this one. How do we measure intensity? With a unit called the decibel, abbreviated dB. So we may have heard that before, that term. So the higher the amplitude, the greater the intensity. And we just talked about that. So the greater the amplitude, the greater intensity, the more energy the wave is carrying. So the further the distance we are from the source, remember the distance from the source was the other factor that determined the intensity of the sound, the lower the intensity. Of course, that means if we're closer to the source, that's going to mean higher intensity. Okay, let's talk a little bit more about intensity, okay, and the decibel scale. So for every 10 decibel increase, the sound intensity is 10 times as large. So a 0 decibel sound can just barely be heard. A 20 decibel sound has 100 times more energy than 0 decibel. You're like, okay, well, it's only a difference of 20 decibels. Why is it 100? Remember, we said for each 10 decibels we go up, the sound intensity is 10 times as great. So we're multiplying by 10 each time. So it's not 10 times 2, but it's 10 to the second, or 10 times 10 is great, or 100 times greater. 30 decibels compared to 0 decibels, we're thinking 10 to the third, right? Because we increased 3 times. We went from 10 to 20 to 30, so it would be 10 to the third. Or 10 times 10 times 10, which would equal 1,000 times more energy. Or, as our ears would interpret it, 1,000 times as loud. Okay? And so let's just take a quick look at the decibel scale and some different sounds that have different decibel levels that we might be able to relate to. Okay, so You know, we start 0 decibels. Remember, that's something we can barely hear. Leaves rustling 10, whispers somewhere between 20 and 30, and so on. We go up, quiet offices 40, normal conversation about 60 decibels, vacuum cleaner about 70. And notice when we get to about 85, that's what's considered loud, okay? So anything over 85 decibels, so interesting fact, for every 3 decibels we get over 85 decibels, the safe exposure time to that sound is cut in half. So like if it's 85 decibels, safe exposure time 8 hours, right? 88 goes down to 4 hours. Go up another 3 decibels, 91, safe exposure time is only 2 hours, okay, without any protection. We can see we increase as we increase, okay, so there's some different things that have different decibel levels, like loud traffic, like 85, mowers 90, we go up to like 100, think of like a snowmobile, sporting event somewhere in between 100 and 110, chainsaw, jet ski, 110 decibels. And remember, as we increase, we can see that our safe exposure time goes down. So if we have no ear protection, let's say we're at a, like a concert, 106 decibels, less than 4 minutes of safe exposure without any ear protection. After that, then damage begins to be done to our hearing. All right, so the key here is when we get sounds that are louder than 85 decibels, we want to have hearing protection, okay, to increase our safe exposure time. All right, so we can see as we get higher and higher, right, we get jet engines somewhere between 130, 140 decibels. And remember, okay, how the scale works. So, we go from, let's say, 100 to 140. You think, okay, that's only 40 decibels, but remember, it's not just it's the intensity increases by 10 times, right? A factor of 10 each, like we multiply by 10 each time. So if I go from 100 to 140, remember it's not 10 plus 10 plus 10, but it is 10 times 10 times 10. So the difference between 100 and 140 decibels, right, it's 10 times 10 times 10, right, or what we call 10 to the 4th power, which would be 10,000 times. So a snowmobile, right, or a rifle blast, 140 decibels, is 10,000 times louder, 10,000 times as intense as the snowmobile is at 100. And we can see, different levels. Okay, rocket launch, 180 decibels. So just give you an idea of how different sounds compare to each other on the decibel scale. Again, we get above that 85 level, we want to have hearing protection. You see, as we get higher levels here, our exposure time goes down, like our safe exposure time. You can see 130 decibels, we better have some hearing protection, right? Because less than 1 second without it, damage is being done to our hearing. All right, so let's go back to our notes. Again, we've been mentioning that loudness is our physical response to how our body, okay, our ears, our brain interprets the intensity. So loudness is the physical response, the loudness of the sound. Again, loudness is directly related to intensity, and also the health of our ears and how our brain interprets the sound waves. Okay, so we've had some hearing loss, and certain sounds are the same decibel level is not going to sound as loud to us as it would to somebody else. Okay, so again, greater intensity, greater loudness. Okay, louder sound. All right, so let's talk about frequency and pitch. So frequency we've had some discussion about already. Remember frequency, which we had measured in hertz. We talked about that's a number of cycles per second, right? Remember 1 hertz equals 1 cycle of a wave per second, right? So remember 1 cycle was a peak and a trough. So the number of those cycles that pass the point in a given, in 1 second, that determines the frequency in hertz. And so again, the frequency is going to depend on a couple things. So first of all, it's going to depend on how fast the source of the sound is vibrating. Remember, sound waves are vibrations of particles in the air. And we're going to talk also about how frequency is related to wavelength. Remember, they're inversely related. So the higher the frequency, the shorter the wavelength. Okay? The lower the frequency, the longer wavelength we have. So with that said, let's think about tubes and instruments. Okay? So certain instruments have higher frequencies, certain instruments have lower frequencies. And the reason for this is because of what we're going to talk about here in a second. So the air in the tubing of a brass instrument forms a standing wave, which we've talked about before, and a longer tubing makes a standing wave with a longer wavelength, but a what? So if I have a longer wavelength, what does that mean for my frequency? Remember, inversely related, so longer wavelength should mean lower frequency. All right, that's also, we're going to see frequency is related to pitch. When we say high frequency, we mean high pitch. And we're going to see pitch is how our body interprets, or our brain interprets the frequency. And it says French horn can produce lower notes than a trumpet because it can make a longer tube for a standing wave. So here's an example of that. Okay, we have a longer tube here, and we see how this sounds. And then slightly shorter tube. So what we notice there is a higher frequency because the shorter tube has a standing wave with a shorter wavelength. Remember, shorter wavelength means higher frequency. And then the shortest tube has even a higher frequency because it has an even shorter wavelength. So, longest wavelength, lowest frequency. Slightly shorter wavelength, higher frequency. Okay, and then even shorter wavelength yet, and higher frequency yet. All right, so let's go ahead and look here. So again, pitch is the frequency. Again, pitch is directly related to frequency. So it's the frequency of a sound as we perceive it. Okay, so as our brain interprets it. High frequency sounds obviously are going to have a higher pitch, and low frequency sounds are going to have a lower pitch. Pitch can also depend on our age, because we're going to see in our next segment how the range of frequencies we can hear, the range of pitches we can hear, kind of decreases with age, and also the health of our ears. All right. So let's just look at quick comparison here. So that would be a sound at 440 hertz. So I want you to notice, okay, the wave, the drawing of the wave here, the diagram of the wave. So that's 440 hertz. So let's go up to 880 hertz. So since it has higher frequency, what should we expect for the wavelengths? So we go to 880, and we can see that there's a shorter wavelength. Like if I look at the distance between the peaks, it's a lot shorter than on the wave that represents 440 hertz. So higher frequency, we should expect what kind of pitch? Higher pitch, right? So let's listen. Okay, so again, we interpret 880 hertz, higher frequency. Our brain, okay, interprets that as higher pitch. Okay, and this is Mr. Pete signing off until our next segment.